So previously in Chapter 16, we've looked at electric charge and electric forces. Now I'm moving on to cover the final segment, which is called the electric field. An electric field is defined as any region where an electric force on a charge can be detected. So basically any region where this electric force is present. An object with charge, as you may remember, can produce an effect without physical contact, meaning that it's a field force. And in a situation with an electric field, we set this force, E, we'll call it, that's the field, equal to the magnitude of the electric force acting on a charge divided by the quantity of that charge. So that's E equals F electric divided by Q sub O, which again, this is the charge. And the direction of this electric field will depend on the sign of this charge, so on the sign of Q sub O. You probably remember from the last segment that Coulomb's law states that a force is equal to Coulomb's constant times the product of these two charges divided by the square of the radius between them. Now, we're going to combine this with our expression from the last page, which states that an electric field is equal to the electric force divided by the charge, which we'll call Q sub O. As you can probably see, these two F's match up because this F also represents electric force. So we're going to plug it in to solve for a new electric field equation. We now get that E is equal to Coulomb's constant times these two forces, or charges, divided by the radius squared, and then this Q sub O is still on the bottom. So as you can see, the two Q sub O's cancel out, and we get that electric field is equal to Coulomb's constant times this charge divided by radius squared. And the radius would be the distance of the object away from the charge, and you're calculating sort of the strength of the electric field on this object. So as you can see from this equation, the electric field depends only on the charge of the object and the distance from that object to another point in space, which is probably the point where the second object would be located. Here are some diagrams that are used to represent electric fields. We use sort of a system of circles and these field lines, which are the lines emanating from the circles. Around an isolated positive charge, we draw the lines pointing away from the charge, as I've done on the left. Around an isolated negative charge, the lines will point toward the charge. And in these drawings, the number of lines is proportional to the field strength. So I've drawn each of these with 8 lines, which means they have the same field strength. Here are some special cases for drawing fields. The first is the electric dipole. This occurs when we have a positive and negative charge next to one another. So with the positive charge, these arrows will point away from the charge, and then eventually they'll start to kind of get drawn towards the negative charge, resulting in new arrows that point toward the negative charge. That's sort of how the two charges would flow together, showing their attraction to one another. In a situation with two positive charges, we would again have arrows pointing away from both charges, but they would begin to repel one another as they point in their respective directions. So none of these arrows would ever cross over one another because the two charges are repelling. Here are some practice problems with electric fields. Number 1. A proton, which has a charge of about 1.6 times 10 to the negative 19th coulombs, and an electron in a hydrogen atom are separated on average by about 5.3 times 10 to the negative 11th meters. What is the magnitude of the electric field set up by the proton at the position of the electron? So we'll be using our rule here where this electric field is equal to Coulomb's constant times the strength of the charge divided by the radius between the objects squared. So we're solving for the electric field. Coulomb's constant, again, is 8.99 times 10 to the 9th. Then this first charge is the charge of the proton, which is 1.6 times 10 to the negative 19th coulombs. That would all be divided by the radius between that proton and the electron, which we've been told is 5.3 times 10 to the negative 11th meters, and that would be squared on the bottom. If I simplify all of this, I get that the strength of the electric field is equal to about 5.12 times 10 to the 11th newtons, and then the units would be newtons per coulomb. Number 2. For the electric field drawn below, A, determine the ratio Q1 over Q2, and B, what are the signs of Q1 and Q2? So we'll start with part A, which wants us to determine the ratio of these two charges. So I mentioned before that the number of arrows or lines that are drawn in a diagram are proportional to the strength of the charge. So in this case, for charge Q1, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 arrows. In Q2, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 arrows. And we know because the arrows are pointing away from Q1 and towards Q2 that these two will have opposite signs, which makes the ratio negative. We'll call it negative 15 over 9, which will equal negative 5/3. Part B, what are the signs of Q1 and Q2? So I told you that when we're drawing these diagrams, arrows pointing away from a charge will mean that it's positive, while arrows pointing towards a charge mean that it's negative. That means that Q1 is positive and Q2 is negative. So this has been Chapter 16 of Physics, where we've covered electric forces and fields. Thank you for watching.